Awesome. Thank you very much. I apologize for the wrong fonts in the presentation. So I put some efforts in selecting the standard fonts, but for some reasons, even standard fonts can be corrupted when transferred to different device. Today, I'm going to talk about something that probably quite far as well from, as many previous speakers were mentioning, from the expertise or interests of this audience. But I would like then maybe it will give some food for discussion and for thinking about what can be done by combining our expertise. And I will be talking about computational catalysis as the bigger field and what kind of challenges we have at this moment with increasing understanding of the dynamic behavior and the importance of the metastable states that are being formed when the reaction is outside of the equilibrium under the catalytic conditions. And in general, the whole idea of computational catalysis follows very simple idea, and it's a dream of both scientists and university bureaucrats, because chemistry departments are usually extremely expensive, and most of the universities want to cut the costs, and by putting everybody to sit in front of the computer. So instead of the clumsy, dirty, and unsafe experimental environment, to put everything onto the Azure or Amazon cloud and have all the answers resolved to us. So this is the dream that people are discussing, people want to put together. And generally, when people are talking about the digital catalysis or computational catalysis that will help us to transform how the chemistry is done from the phenomenological science into something predictive, they think that we need to put together the efforts of spectroscopic characterization. So we had several talks on spectroscopy applications to material sciences, and that's exactly the same in catalysis. So we need to do spectroscopy to characterize the materials that we are using in catalysis, simulate the spectroscopic signatures to get the structures, the structural information, the electronic properties, and then use it to describe the actual key performance indicators, performance measurements that we have in catalysis. And these are kinetic features and reactivity patterns. The big difference between the material sciences and catalysis is that material sciences is looking at the static, most of the time, quite static or thermodynamic ensembles that are not evolving in time. At least you can fix them in time. In catalysis, you never work with static. Static means the dead state or the state that precedes the catalyst. And that creates the biggest challenge for understanding how it all works. You have to work with something that is not thermodynamically described, that has a time dependency, and finding the descriptors that we are obtaining, the things that we want to correlate with this reactivity that is time dependent, is the basic characteristics of the material in the cupboard that you have. I will come to this a bit later. So there is this big challenge, and in my group, we work with both heterogeneous and homogeneous catalysis. Heterogeneous catalysis, it's the reactivity of the surface states on the materials. And this is, as the name suggests, that usually refers to the phases of the catalyst and the reactants. So the heterogeneity of the interface is also reflecting the state of the catalyst surface that is extremely heterogeneous. So the problem of designing or understanding heterogeneous catalysis is very, very large. Therefore, in this particular talk, I will look at something extremely simple. I will be talking about homogeneous catalysis, where you know exactly what you put in the reactor, where you have at least no uncertainty. You can minimize uncertainty about the starting state of the reaction, and that creates for you a possibility of designing the catalyst space, designing the catalyst, and making the connection between what you have in the reactor and what you have in the cupboard. And from the perspective of homogeneous catalysis space, what do we need to navigate to find a catalyst? It's very straightforward. We talk about transition metal catalysts. So we have metals from the periodic table. This is one part, and that's the reactive center. So the properties of this metal are key to understanding, in principle, the key in the whole field of homogeneous catalysis, and their properties are controlled and impacted by varying the organic environment around the catalyst. So this introduces some minor modifications into the behavior of the metal. So you can, in principle, very nicely map and define the catalyst space by combination of the properties of the metal and the properties, structural and the electronic properties of the surrounding ligand atoms. And just to reiterate once again, the fundamental goal is to connect the library of the static materials that you have in the glove, in the cupboard in your lab, that you want to put in the reactor. So I have here. So this is just the cupboards You know the structures, you know, you can have a crystal structure for the materials, so you know exactly what you have there, and you want to measure them. You can measure, I don't know, any type of characteristics, any spectroscopy on these materials. That's not a challenge at all. And then you want to connect the properties of these materials that you can tabulate, document, with the response that you will be observing when you're exposing these materials to your catalytic reaction action. So basically how quickly they convert your reactants into products, with which selectivity and so on and so forth. The basic, this works. There are many, many papers that claim, and this is sort of the basis of the theory of homogeneous catalysis, that says that there are already predictive theories for this, right? We have this type of a volcano plot approach that started from the Sabatier principle. Basically, you are trying to correlate the kinetic response function, so the kinetic information, the rate of the reaction, with the binding energy of particular substrate or particular reactant with your metal center. So the binding energy is intrinsically a thermodynamic property, so it's time independent, and you correlate it with the rate response. Even though nobody have said that there should be this correlation, for 100 years, we have observed in chemistry that there is. So there are many success stories, and for example, I mentioned here the work of Cormenbuv, and Balcel has wrote a very nice review on this topic very recently. Here, scientists are using a mechanistic understanding, so they know how the mechanism of the reaction works. They identify a rate determining step, and they say that for this rate determining step to proceed with the rate that we want, so that other reactions are not outperforming or not hindering this rate determining step, we need to optimize the particular bonding characteristics. So you need to have an understanding of how reaction works to have this. It's sort of mechanism informed predictive models. More recently, there were moves into mechanistic agnostic type of predictive models, where people just taking all possible descriptors of the ingredients of the chemical reaction space that you start from, so characteristics of the metal, of the ligand, it can be electronic, structural, you name it, put it in some neural network and make a model that will also show a very nice graph, and they will start explaining that it's all predictive. So this is the works of Matt Sigman, Abby Doyle, and it's connected to high throughput experimentation. So you increase the amount of data, and you can claim that you don't need to have any mechanistic understanding to enable this connection. In a nutshell, the process of how you connect the static properties of your starting material, so your component of the catalyst space, with the reaction response proceeds through this approach. So you draw some structure, you identify the structure, you have the initial, you say how your catalyst structure will look like. You do DFT calculations or any other chemoinformatic, you employ any chemoinformatic approach to extract the chemical properties of this state that you create, that you expect to have in the library of your catalysts. And then basically the fundamental idea of why thermodynamics should correlate with the experiment is coming to just this intersection of two harmonic potentials. So what in all of these approaches you anticipate that your kinetic response, that is a function of the barrier for the particular reaction, will change if you start changing the thermodynamic parameters. So basically the location of this parabola. If you move it down, assuming that the starting point is the same zero, intersection between the two harmonic potentials will go down as well, resulting in the lower activation barrier. If the final state is less thermodynamically favorable for the reaction, so if some thermodynamic response is having a different, is more positive, so this parabola goes up, the barrier will go up proportionally. So this is the fundamental basis for almost all structure-activity relationships that you can see in the catalysis field. And as a result, you get some plot like that. You say that these are just exceptions, and you have a perfect straight line. This is how people normally do. And that's how they publish in Science, ACS catalysis, and chemical science papers. I am not as smart as my colleagues who are very successful. I am approaching the field differently. We have resources. We are strong. So we decided to look at it, to increase the amount of data and to see whether we can generalize this approach and see where it fails and why it fails. So try to understand what doesn't allow us to fix, to put the square into the circle. And today I will be talking about one type of reactions just to make it very simple. So it's homogeneous catalysis. And we will be talking about catalytic hydrogenation chemistry. And it's a very, very broad field with a lot of applications. In the context of Europe, it's the implementation of the hydrogen economy. So the green hydrogen application for the chemical synthesis. Hydrogenation reactions include also CO2 hydrogenation, so all type of C1 chemistries and converting the greenhouse gases into something useful. So there are a lot of applications, a lot of things for circular economy. So we can put a lot of sentences in the introduction paragraphs about it. But there's also very nice synthetic chemistry that allows us to replace what is commonly used in pharma and organic chemistry, like lithium aluminum hydride and other inorganic stoichiometric agents, with very atom efficient hydrogen molecule as the reducing agent. So coming back, we want to do that. So what we did, we decided, let's make it simple. We are not that smart, we are not that genius, we have resources. So let's look how this direct approach of taking thermodynamic characteristics of our catalyst will correlate whatever we can find. We'll be correlating with the response, with the reactivity response of the real experimental catalytic reactions. And to minimize the number of unknowns, we decided to look at the most simple example that we could find on paper, on the textbook chemistry. And specifically, we will be looking at the rhodium catalyzed asymmetric hydrogenation. Who studied chemistry? Good. Who remembers major minor principles in anti-selective catalysis? That's the wrong audience. For all mechanisms in this particular chemistry, an anti-selectivity, so the choice of what kind of products are, so you start from asymmetric precursor, you put a hydrogen on one side, and in anti-selectivity, there are many discussions about the mechanism. The product of the reaction will be defined by how the substrate, this prochiral substrate, will bind to the metal center. So the response, the anti-selectivity, is by definition, is a function of thermodynamic, the preference of binding of a particular substrate. So there is no time dependency. So from this perspective, this particular model system is perfect for our analysis. Basically, this is our metal center. This is our rhodium catalyst. It's a square planar rhodium catalyst having the hydride having an X, I think it's square planar. I'm not sure, I don't remember anymore. So, and this is your prochiral substrate. So you see there are different substituents on it. And if you coordinate this double bond, it comes flat to your metal center. And then the hydride has to move to the double bond. That's the start. And if you put the molecule like that, the hydride will come, and then all the rest of the reactions will proceed to the molecule where the two hydrides will be on one side. And if it binds on a different side, they will go from the other side. So very straightforward. And there is this type of chemistry which says that the nature of the ligand, so the second part of the catalyst space, is providing you a very specific geometric environment around this metal center that defines the preference of your substrate to bind this way or that way, right? There is a discussion if the most preferred coordination gives rise to the major product, or there is a discussion it's a minor, preferred will give you the lowest barrier. But these are details, the mechanistic details. The fact is that there should be a very strict correlation between the preference of binding and, as to start even earlier, with the type of the geometrical environment that is realized around the metal center and the preferred binding configuration. So we need experimental data for that. It's a textbook chemistry. There has been a Nobel Prize for it, and it's more than now 50 years old chemistry. So there were thousands of papers studying it and reporting. So one could just take data from the literature and create these correlation models. We first looked at the reaxis and we found out that most of the experimental chemistry is success stories. So if you want to develop theory of chemical reactivity, the chemistry reports of the last century are usually not very promising because most of the reports in chemistry as the discipline are focused on reporting success. Chemistry is the science of making things. So if you didn't manage to make things, it doesn't worth reporting. as a result, the data sets are very much skewed towards the highest conversion and the highest selectivity. So instead, we went to our friends in Janssen Pharmaceutical who have amazing machine that can run 96 reactions at the same time. They just run several reactions with very good reproducibility, and generated a much more diverse data set for us. So this is how it looks like. It's a beautiful piece of engineering. Right, it's reproducible. So there's another thing in academic chemistry labs. You do not try to repeat successful experiments just in case. Here, different people can run it and it works because the protocols are very good. This is pharmaceutical industry, right? What we did on our side, we created a workflow where we would calculate the properties of the precursor that we know how it looks like, we know how it is formed. We would generate them in silico. Again, I'm working in chemical engineering department. Students who work with me do not know chemistry too well, so they need to have some machine that would automatically generate stuff. They don't have the feeling of chemistry. And we calculate different descriptors for this metal-ligand combination and try to build models. The workflow that we have made combined several Python scripts. We start with defining our catalyst space, which is we select a metal, we tell which coordination environment it should have, which coordination polyhedron it has, define the ligand scaffold, say what can be substituted there. So it is just you write it down, you write a SMILES code, and you identify what will be the ligand. And then the machine uses the epic maze. We called it maze before the machine learning potential maze has been introduced. So that creates a bit of, but we were earlier. It's called now epic maze. It is converting the 2D graph to any possible stereoisomers for the transition metal complex. So it generates automatically the 3D structure from 2D. And that also, I will be talking about it a bit later. Then we have the ChemSpax chemical space exploration platform that allows to modify and functionalize the ligand. So it's also the Python library. And then there is an Obelix that is calculating all type of descriptors from the complexes that you are producing. We can integrate it with the data set that we obtained at Janssen and then correlate. I will skip this PCA analysis that shows that, yeah, we encode we can have chemical information encoded in this data set. And to just come to the end of this talk, if you just put very well prepared experimental data set with very well prepared and curated computational data set, the model that you get from DFT computed descriptors will be not much better than a random number generator. In principle, I could have made this talk and I could have manipulated the data in such a way that it would have been a success story. I would say that we have to exclude this part of the data set because it is an exception. I would add some heuristics based on my understanding of the chemistry, and then it would be a success. There is sufficient number of data and sufficient number of descriptors to make an elephant fit the square. However, we didn't do that. We decided to think, why would this direct data-driven E prediction fail? And we came to a conclusion that the biggest problem there was the models that we used and the representation. Here is the spherical cow that I like a lot. The starting assumption was that when we are generating the catalyst, the structure, and that's what we are all learning in chemistry classes, the structure is the key function that defines the performance. So the fixed structure that we can get from the XRD or the structure that we are getting from the geometry optimization, the global minimum, will be the proxy to whatever functions, the performances that we will be observing. So there is a very big complexity challenge. We do not consider that the catalytic properties of the material can emerge upon the interaction of what we had in the cupboard with the reaction environment. We completely ignore that. We think that there is no emergent behavior, and we expect that there is some correlation that will be present as such. We also say that the structure, our global minimum, is defining all the properties. So we are fixing it, and we are calculating the descriptors for a fixed species. But reality for the reaction. So the performance is basically the non-selectivity that we talk about is basically the difference in the activation barrier between these two reaction pathways. And this picture nicely illustrates conceptually why we fail when we try to make this connection. The descriptors of our structures in the cupboard are basically something here. Before it enters the catalytic reaction and can go through these barriers and select the pathway towards one enantiomer or another, is defined quite later. So after it was exposed to the reaction medium, you form some species, so there is an emergent behavior. The dots that I show here, it is the fluxionality. So there is not one minimum, there is not only one minimal path, but there is a possibility for this molecule to change conformations and configurations during the reaction. And each of these components can have a different reactivity, and they can contribute to the reaction differently. We do not include that. So the model, the static model, that is based on the global minimum in the static environment before it touches the reaction, is seemingly the problem. How there is a very low charge level, and I would expect, I would like somebody to plug it in, and I will do it myself. Right. To test that, we looked at the, so we start with this model system. So this is what we have in the cupboard. There is a rhodium complex with an non-monadiene sort of placeholder. It's a symmetric molecule, and it has been chosen because this is experimentally what we have as a catalyst precursor. From computational perspective, it's a nice symmetric molecule that fixes the ligand environment. So it allows us to get all the descriptors with as little uncertainty as possible. The substrate is the alkene molecule with the substituents. And depending on how it positions itself in this quadrant, will define the enantioselectivity. So for the substrate, there can be 4 different locations, where 4 different configurations in which the substrate can coordinate. For NBD, it's only 1. So it's already an illustration. You already have an answer. This model does not encompass information about this potentially. When we did the analysis of the fluxionality of how many configurations there are, depending on the type of the molecule that we coordinate to our metal, we found that our non-Bordendiene, this locked pre-catalyst structure, doesn't have much conformational freedom. So most of the, it was selection of 11 ligands that we analyzed. You can see that there are not that many conformers that can be realized for this structure. So the substrate basically locks the environment, and that's what we wanted. But when you expose it to your reactant, some of the structures can suddenly exhibit much larger number of conformers just because of this interaction. What is interesting, these conformers, it comes not from the substrate conformers, but it's the ligand conformers that change. So the fundamental properties of the catalyst, the ligand, the catalyst space changes upon the interaction with the specific substrate. Yeah, this is how it, so the substrate variability is very low. It is the ligand variability that increases. The impact of this is quite large. It impacts not only the structural descriptors, because you have these different conformers, but you also have a very strong impact on the electronic properties that you would expect, not that much dependent on the conformers. So this is just a HOMO-LUMO gap that we calculate. And you can see that for the green lines, you are basically quite fixed, and you are having a particular level for all ligands, quite close. Depending on the S substrate, how it coordinates in the major and the minor, that's how we call the different configurations, the HOMO-LUMO gap can start jumping all over the place. So this is already an illustration that our initial assumption, this attempt to connect, is wrong. You have to, if you want to predict how the catalyst will behave with particular substrate, you need to calculate it already with the substrate and calculate a very large number of structures. Now, a quick question. How much would you think one catalytic experiment with rhodium catalyst and anti-selective catalysis would cost in a high throughput lab? A ballpark in euros. 10 euros. 10,000 euros, one experiment. They do 96 reactions at once. It's €1. It's 100 euros per plate. How much would it cost to run one DFT calculations, one of these complexes with rhodium at DFT, let's say PBE 0 triple zeta? How many CPU hours? No, there is a price. So you can convert CPU hours into the commercial price of the supercomputer. And my estimation from 2 years ago was around 10 cents. But it's one structure with one fixed parameter. If you want to include conformers, you will multiply it by the number of conformers. If you want to calculate transition states, or if you want to calculate substrate-dependent features, you will very quickly come to the point that your calculations will be as expensive as running the experimental high-throughput setup. Oh my God. We lost the nice pictures with the cats and castles. But it's okay. On top of the conformers, there is also something that we always assume. So you always assume that there is a particular coordination environment that is being formed, and it's universal for all different complexes. And most of the time in mechanistic proposals in catalysis, you say that for this particular metal, you will have this mechanism. And when you move to a different metal, you will just say that, let's assume that the mechanism doesn't change and the coordination environment doesn't change. So there's also an assumption. And moreover, we always have a preferred coordination environment. We also say that depending on the ligands, the basic coordination environment will not change. We always say that the ligand is changing, introducing minor modifications to the reaction environment. If you don't have these assumptions, you may also consider that when you're mixing ligand with the metal precursor in your reactor, you are not defined by only one stereoisomer that is formed, but in principle, you have to consider 30 stereoisomers. So this is how the different ligands are coordinated to a metal cell. So we also tested that, and we found out, we used this maze to generate all different stereoisomers, and we just compared these three different metals with 96 different bidentate phosphines, and we looked at how many thermodynamically accessible different stereoisomers can be realized for different ligands. And we found that in about 80% of the cases for ruthenium and manganese, you will find that upon mixing, you will not form one catalyst, but you will form multiple catalysts. For iridium, just because there are only two options, there is a preferred one, but even there, 30% of the cases will give you a diversity of catalytic species in your solution. So the starting assumption that there will be a structure that is connecting from the cupboard, connecting to what is happening in the reactor is already not true. There are multiple possibilities, and all of them will be condition dependent. Interestingly enough, it is a problem for catalysis, but it's not a big problem for optics, for example. In optics, there is no time dependency, so your structure will be directly correlated with the optical response, right? So there is no time dependence. And interestingly enough, a lot of machine learning models and DFT successes in the optics are because this structural flexibility, I had here also some animation. This red is a good correlation between different configurations. So you see that the bite angle, so the basic structural environment, what the ligand provides, the first coordination sphere, is correlated, so it doesn't matter which configuration you have. But most important, your homo-lumo gap, so the optical response, it doesn't feel how this environment is arranged. What is important for our stereochemistry is the local charge on the metal and the stereochemistry around the metal. And these are extremely sensitive to these minor changes. And that explains partially why we failed to use our direct approach. To summarize it, this first part is that in homogeneous catalysis, the definition of the metal and ligand as the basic ingredient of the catalyst space is insufficient because it doesn't give us one defined catalytic center. So in principle, you have to consider a catalyst as a dynamically evolving ensemble of species that is created upon the interaction with a specific reaction environment. Which means that if you want to predict, we want to have this connection to our reaction, we have to consider all different options that can be generated for every particular reaction. And that increases the number of calculations that we have to carry out, increases the number of descriptors, and makes the whole exercise completely useless. Because you will be limited in predictions to a particular selected substrate, so you cannot create a prediction based on one substrate for another substrate. And also it's metal dependent, it's ligand dependent, it's dependent, everything depends on everything, as some of my experimental colleagues were saying. And DFT is not very good there because it becomes extremely expensive. Of course, we are now living in the times of artificial intelligence, and machine learning will definitely save us. What we found that the problem of the speed of the calculations is very easily addressed with the modern machine learning potentials. And we are particularly happy with the UMA as the UMA and the MACE for heterogeneous catalysis. MACE works better. UMA is fantastic for homogeneous catalysis. And there were very nice papers by Markus Reyer group on the implementation of machine learning and AI, machine learning potentials in catalysis. So Markus, for example, has just put on arXiv a perspective where he claims that we are now witnessing a revolution in computational chemistry because he expects, and the community of machine learning potentials expects, 4 orders of magnitude speed up of standard geometry optimization tasks. So then structural problem is solved. We did our own test on a laptop of my PhD student who spent first 3 years of his PhD calculating all these complexes and getting all the structures and everything. And we spent quite a lot of computational resource on these calculations. He just took the whole data set, put it into his laptop, and within a few hours, he's got energies and structures. And this is the plot for the energies for one of the data sets. So the speed up is there. Structural problem is solved. So we can speed up the calculations of the structures. So it will be only the single point to extract the descriptors if you need them. But there is another problem of the representation, because we are always dealing with a graph representation that doesn't have dynamics in it. And we are also working on this part, and I don't have time to explain this. We were working with Ivan Bushmarinov, who is now in Perplexity, actually. And we just got a paper published where we are discussing generating representations in the machine learning context instead of graphs based on the 3D structures. So we have introduced based on the Unimol backbone, we introduced a new contrastive objective where we taught the machine learning system to understand conformers. So I was talking just now about the structural diversity, that the molecules are flexible, right? And I said that in order to understand reactivity, you need to start understanding how the conformations change. And this is the example of something that I find very intriguing and very interesting. We wanted the machine, this diffusion model, to be able to distinguish between conformers, different conformers. We trained it. So normally in the 3D structure, the model learns how the molecule looks in space. So the original Unimol model trained on the very large number of 3D structures was able to differentiate. So you see these 3D molecules are looking similar. So it was distinguishing the conformers. But when you were giving it isomers, it could get confused. So Unimol original's data set, where you didn't have this contrastive, when you didn't teach what conformers are, would not be able to distinguish this molecule from this one. For those who are chemists, could clearly see that these are very different molecules. Oxygen is here, for example. When you teach to distinguish conformers, it starts also understanding what isomers are. So when you teach a machine, like with a student, you teach what the conformers are, you also will have to explain what isomers are, and it sort of understands how the chemistry works. To our surprise, it learned much more. So it was written there. What it learned not only how to understand what is conformer, what is isomer, it also learned how to predict better the quantum mechanical descriptors. So there are benchmarks, pharma benchmarks and quantum chemical benchmarks. And when you taught the machine to understand conformers, it suddenly started predicting better all the descriptors and all the properties. And that's for me something very interesting. I do not know what to do with it yet. But it seems that like with the normal chemistry education, understanding the conformer isomery, the isomery in general for the machine, and creating representations that contain the information about the isomers is critical to understand, to create a predictive model capable of predicting the response functions. So we were so far talking only about the structures, right? How they interact on the structural level. But when you are doing the actual reaction, you go from substrate to a product. There is a supercat drawn by my daughter. And the function is not only how it converts substrate to product, but there are more other parameters. It's not only the reaction from here to here, but it's also the good catalyst maybe would be fantastic for the rate determining step, but it doesn't form. So the path from catalysts to it didn't realize. Or it would have a fantastic reaction to the product, but also would deactivate quickly. So there are much more parameters for the reaction itself that you need to understand and have somehow capture in your model to be predictive. And in the last part of the talk, I want to show you a few slides, and it's completely collapsed, all the slides on this laptop, because next slides don't have any pictures, but I will explain. So the main message will be, you are theoreticians, about the ground truth for us. Because we, when we create these models, when we calculate something, we need to compare them with something, right? So we all discuss about the accuracy of the DFT. What is the accuracy of DFT in energy? How much? Awesome. What is the accuracy of the experiment? Of a catalytic reaction when you measure reaction rate. What is the accuracy? How do you define it? And that's something that I want to talk about. I will skip all the slides. We are now change gears. We will talk about ester hydrogenation, much simpler reaction, no unanswered selectivity. We're just putting hydrogen across here and make two alcohols. And I was very lucky in 2017 when I learned from Matthias Beller lab that manganese works. Everybody else was doing ruthenium. They suddenly told us that manganese worked, and we were one of the first ones to find one of the manganese catalysts that works. That is one of our first attempt when I was still at ITMO, collaborating with ITMO, first attempts to create a machine learning model where we tried to collect all the information from the lab journals and to figure from the initial attempts of the whole community to find the good manganese catalysts. So they were combining ligands and the metals, doing the reactions, and we were trying to correlate chemoinformatic parameters with the turnover frequency, reaction response. What we found that all these people didn't test the catalyst, which is green. They tested the conditions of the reaction, basically. So we were first, with how we started. We had some ligands in the lab. We had some precursors. We tested a few. We found that this one works amazingly. Not very in the first test. This one works perfectly, but we couldn't isolate it. So we started working with this one because it was easier to publish. And we found that the yield of the reaction very strongly depends not on the catalyst, but on the addition of the base. So in this picture, you can see this in the feature importance plot, you see this additive concentration. So you have a reaction, you have a catalyst, temperature, whatever things, solvent. But for this reaction to work, you need to add an organic base. And that's a very important component of the reaction that is not part of the catalyst space, right? It's an additive. And if you look at this picture, you will see that if you don't have any base, there is no reaction. You need to activate the catalyst. It's an activator. But you have to use a very huge excess of this base to make the reaction go to completion. So your catalyst remains the same, but the fact that the reaction goes to completion depends on how much base you put in the system. And it also relates to this particular picture. You have the catalyst, it needs to activate, and it uses the base, and then the reaction can start. And during the reaction, your product can inhibit by forming a stable configuration. So we started looking at, can the base somehow affect not only this part, but anything around the catalytic reaction? I will skip all the synthetic work. So we synthesized, isolated, so we know exactly what we put in the reaction. And then we build a machine to look into our high pressure autoclave and sample very nicely kinetic information and do spectroscopy at the same time. So this is infrared spectroscopy where we are monitoring the manganese catalysts that are evolving during the reaction. So we start here and then the reaction proceeds, and you can clearly see that initially some vibrational features are disappearing, some new are appearing, and we can integrate these infrared bands and put on one plot. In the blue line is the reaction rate, how it evolves with time. There is clearly a step for activation, so the catalyst is forming. Then it has a linear response and then slowly deactivates. And at the same time, you can plot the evolution of these bands that are corresponding to different species that are formed in the reaction. So what we observed that the initial stage activation is correlated to the formation of this 5-coordinate manganese complex 5A. It works, it does the reaction, so this is exactly this state. The 5A is just running the reaction. However, during the reaction, when you start forming alcohol, it can react with this complex and form this inhibited state 6. So the reaction is getting inhibited by the produced alcohol. And you see, in this equilibrium, there is no base involved, right? In this reaction, there's also no base, although here it was potassium butyrate. So the only place in this chemistry where the base, this promoter, was needed is here. We looked further, so we decided to look at the inhibition step and try to see if base can have an effect on this reaction. To our surprise, once again, this is the reaction. There is a complex 5A, which we can very nicely characterize with spectroscopy and the XRD. We have complex 6, also very nicely characterized. And we can monitor with UV vis spectroscopy how the 5A converts to 6 with time if you add alcohol with temperature. And that allows us to just measure the free energy of the reaction. This is thermodynamics. There is no kinetics, right? Look at this equation once again. There is no base in this equation. However, if you introduce a base, your delta G of the reaction starts changing. So it was very favorable. It goes to thermoneutral. It goes to unfavorable at the higher base concentration. So your additive is affecting the fundamental, the standard free energy of the reaction. You can say you're changing the environment by adding a base, so your system is not closed, but that's not how we write it. You can do from Cosmo calculations, just you can estimate free energy for this reaction, and you will see that theory is reproducing the trend of increasing free energy for this step. What is more interesting is that if you change the ligand, if you change the alcohol by keeping the base, and this is again experimental, free energy is a difficult parameter to calculate. If we are talking about the accuracy of DFT, it's better to talk about enthalpy, which is immediate proxy to electronic energy, right? And thermodynamics is very easy to calculate. So if you plot enthalpy for this reaction, standard enthalpy for the equilibrium reaction, you will see that it's very strongly dependent on the concentration of the base to alcohol, so basically the base concentration. And the change can be for some alcohols and ligands, 12 kilojoules per mole, for others, 26 kilojoules per mole. So depending on the reaction environment to which you introduce your chemical system, you can get standard enthalpies that are measured that will vary by 5 times the chemical accuracy that our community struggles to achieve. So the experiment, depending on the conditions in which it was measured, will provide you with very different numbers. So I don't have answers. We're still struggling of how to figure out these connections. The biggest problem of catalysis is that there are too many factors to take into account. Making fully mechanistic model is possible, that's what we do, but then you optimize one system at a time, and that's not the most efficient way, and most of the systems have been basically optimized. You're like a drunk who are looking, where does the drunk look for their wallet, by the way? Who knows? Under the lamp, exactly, under the street light. And that's exactly what the chemistry community is doing. The whole homogeneous, the manganese catalysis discovery was the use of ruthenium ligands that were used for ruthenium for a different metal. And it worked for some systems, for some it didn't. But we didn't optimize specific ligands for manganese that could have unraveled much better performances. So in my lab, we are tackling this challenge from 2 approaches. We are developing new ways to get better kinetics, better thermodynamics, better ground truth for our mechanistic models. And at the same time, we are struggling to develop dynamic representations of catalysts. So how to encompass this whole diversity, emergent diversity, structural and configurational diversity, and stoichiometric diversity of catalytic systems. In this talk, I will discuss a homogeneous catalyst, which is simple. Imagine now that you're working with heterogeneous systems where your surfaces are formed under activation conditions, and then you have phase changes and segregations and formation of new ensembles while moving from activation to reaction conditions. So the problem is becoming much bigger and much more complicated. And we hope that the machine learning and the vibe coding will help us to solve these problems. So most of the work that I was discussing today was done by Adarsh Kalikarin, who just defended his PhD in March. Mas Klein is my super genius young colleague who will start his PhD in September, but already has some 3 or 4 papers published. I was very lucky to love bomb him and manipulate him and staying with me. Sasha was super amazing in supervising these people, and Evgeny is my super expert in kinetic studies. This is the most important message. realistic chemical systems can give you more than 20 kilojoules per mole variations in the enthalpies that we measure depending on the conditions. So when we are thinking about spherical box, spherical cow in vacuum, we have to always think how spherical was the cow that they put in the reactor. With this, I would like to thank you for your attention, and I will be happy to answer any questions.